A second order reaction will look like. Second order means that if you double the concentration of the reactant, then the rate's going to increase by 4 times. It'll be that change squared. If we triple the concentration of the reaction will, of the reactant, triple the reactant concentration, that'll cause the reaction to go 9 times faster. It'll be 3 squared. So if it was second order, it looks like this is the differential rate law. Rate equals K times the reactant concentration squared. So if we were to do this one as well, make this negative dA over dt. Moving the a's over to one side, it will look like this. 1 over concentration of A squared equals, or not equals, dA. That's equal to negative K dt. Okay, integrate this one. Hot shots.
Wait. So is that a to the negative 2?
That's a to the negative 2. The integral of a to the negative 2.
I don't know if that is just 1 times just 1.
There's 1 over a.
Wait, what? Why isn't it natural log of the negative 2?
It's not.
Okay.
So, now remember that was from, it was time 0 to time t. So it's going to be, actually it's negative, that number, isn't it? It's negative. Okay. So it's negative 1 over concentration of A at some time t minus negative 1 over concentration of A at time 0. That was the initial concentration equals negative KT. So rearranging that whole thing, oops, we would have this. Getting rid of all the negative signs, we'd have 1 over the concentration of A, that's this thing, equals KT plus 1 over A0. So if it's a second order reaction, this gives a straight line. Get your highlighter out. If you had your highlighter out, highlight that part. I warned you today was slow. It goes much smoother the rest of the chapter. There's not going to be another day like this, so please come back tomorrow. You don't have to, but I hope you do. That's right. Okay, are we good with that one? Now let's just jump right to 0 order. You see how these things are derived. If we have a 0 order reaction, that means that the differential rate law would look like this. And really what 0 order means is that the concentration of the reactant does not affect the rate. The rate is independent. You can double that, the concentration of A, the rate's still going to be the same. 0 order. So that would mean that K times A to the 0 power equals the rate. And integrating both sides after we evaluate and make a differential equation is going to give us this. So if we have a 0 order reaction, if you plot A versus time, just the straight up concentration of A versus time, that would give you a straight line.
So determine it to
That's what it means. It doesn't affect the rate.
Yeah.
Yeah. Yeah, the reaction needs to be just as fast as it was before. What was that? That was a catalyst. Yeah. Yeah, that catalyzed the reaction, and that catalyst didn't affect the rate. Because hydrogen peroxide, that reaction right there in red, that happens spontaneously over a very long period of time. Hydrogen peroxide all decomposes. We speed the reaction up a lot by adding a catalyst, and it bubbles up, it gets hot. It's a pretty nice reaction.
So it's a zero order reaction, though, right? Like it doesn't matter how much you have; it's going to decompose naturally, spontaneously.
Yeah, but that doesn't mean that it's zero order.
Oh.
If it was zero order, if you had a real high concentration of it, it would decompose as fast as if the concentration were low. It turns out that that's not a zero order. That is affected by the concentration. A higher concentration of peroxide will decompose faster.
I was mixing up concentration and mass.
Yeah. Okay, so I don't know that you need to write any of this down because you already did. And I asked you to highlight those statements. And this is a summary of what the integrated rate law is. So these equations, these expressions, those are the rate laws, depending on what the order is. To know what order you have, and this is the part that's a drag, take the data and plot the concentration versus time. If it gives you a straight line, that means it's zero order and you're done. But zero order is not very common. So then if it doesn't give you a straight line, which is more likely, then you have to take the natural log of the concentrations versus time and plot that. If that gives you a straight line, that means it was first order. But if it doesn't, then you have to take the inverse of the concentration versus time and plot that. If that gives you a straight line, it was second order. And if none of these give you a straight line, I don't know what to tell you. It's got to be one of them. Once in a great while, you'll come across something wacky like it's a half order. I'll take a half order of pancakes, but I don't want any half order reactions. You'll worry about zero, first, and second. It's going to be one of those three.
So there's no such thing as third order?
That's possible, but not likely. When we actually find out what order really means, you'll find that it's not real common to have a third order. It can happen, but not those. Yeah, integrate.
So you
Run
run
over
over like starting
AQ.
first order, like
First order, yeah. You'll see more first orders than any. So, page 596 has number 47, 43. How are we doing for time? Okay, I want you to see number 43, and then I'll show you how we do it. Oh, that did not do well. Okay. It says the dimerization of butadiene, which is C4H6. Dimerization. You remember polymerization? Those were the good old days, weren't they? A dimer is where you have two monomer molecules and they just join together. It's on the way to being a polymer, but they'll just join together. And when you have two monomers that join together, it's called a dimer. One of those dumb chemistry words that they come up with. So this reaction was studied at 500. The temperature's not going to mess. Sometimes you'll have to use the temperature in an equation, but as long as the temperature's staying constant, then you don't have to worry about that for determining what order the reaction is. So we have some data. The reactant concentration is given here. Notice the reactant concentration is going down. We expect it to as time goes on because it's going that way. Determine the form of the rate law. That's the differential rate law. The integrated rate law and the value of the rate constant K. When you have concentration versus time data, you're going to be able to find the integrated rate law. We cannot find the differential rate law from this data. You'll see when we get to differential rate law why you can't. So I made an Excel spreadsheet of this data, and I want to show you that. I've got a link to it right there. Okay, so I took the times. There are 5 data points. So here's the times and the concentration. This was given straight out of the book. Time and concentration. I made a graph of that. It's right here. And when I graphed the concentration versus time, it gave me that. Does that look straight to you? Linear? Nope, so it's not zero order. So I'm going to get rid of that. And then I took this concentration data, and I took the natural log of each of the points. In Excel, it's easy to do that. If you know how to use your calculator well, then you'll be able to do that quickly on your calculator too. I don't know how to use those things, so I can't show you.
Wait, use what? The graphing?
Do a graph.
Oh yeah, I don't know.
And then yeah, take that data set and take the natural log of each of the points.
Yeah.
So anyway, I took the natural log, and here is a graph of, oops, sorry. Here's a graph of the log versus time. It's got a negative slope. Does that look linear? It's more so than the one before it, but not real linear. So I'm going to just make it a little bit smaller and send it back over there. And then, so that one doesn't look too linear. Let's go ahead and take that original data and take the inverse of each of those points. Plot that versus time. That's right here. Is that more linear? That's our winner, I think. Yep. If you're not sure, if I have some people that say, I think this one is more linear than that, how could we tell? Is there anything that we could do to be confident which one is more linear? What can we do, Wendy? Do you know? You got it. Regression, linear regression. And that would be, if you right-click on any of the data points, you can do this too on your calculator. You go to stat and you do something, I don't know what it is.
Stat plot.
Is it?
Yeah.
Anyway, in Excel, you right-click and you go to add trend line. And the very last thing is display R squared value. If R squared equals 1 for a set of data, that means it's perfectly linear. So the closer R squared is to 1, it's never going to be above, it's always below. The closer it is, the more linear it is. So if we just tell it to display the R squared value, it'll say R squared is 0.985 for the first order graph. And then do the same thing over here. Right click on a point, add trend line, display R squared. R squared equals 0.999. So it's 0.985 for this one, it's 0.99. Both of them are pretty linear, pretty close, but that one wins. So we would say this is a second order reaction, and the integrated rate law would be 1 over C4H6 equals KT plus 1 over C4H6 initial. The problem didn't give us what the initial concentration was. Could we find the initial concentration? I think we could, because another thing that we can do is show the equation. Did it show the equation before? It tells us that we have linear. Where does it say that? Oh, display equation on chart, sorry. It's right there. So if you tell it to display the equation, it's right here. Ugh. They did it right over the top of the regression. Anyway, the y-intercept is there, and that would be the initial, well, the inverse of the initial. Remember, the y-intercept is 1 over A0. So once you get the y-intercept from the calculator, from your Excel, then just take the inverse of that, and that'll tell you what the initial concentration was. So these things are very powerful, and they're real nice. That's what we had to do, though. Talk about tedious. Just to find out what is the order of the reactant, you've got to make 3 graphs. Unless you have one that you can tell right off the bat is a straight line. Otherwise, go ahead, Shirley. Otherwise, you make it 3 graphs. On the test, am I going to expect you to do all this and then make 3 graphs and do several other problems? No. I would shorten these problems for you by